So today, we're going to talk about the surface integrals, not of multivariable functions, but of vector fields. And remember that the distinguishing difference between a multivariable function and a vector field was that a function produced a number and a vector field produced a vector. So we're going to define the surface integral of a vector field as a double integral, and then this quantity is also referred to as the flux, and we're going to calculate flux over some very simple surfaces. So the first thing that we need to establish before we even get started with flux is the idea of the orientation of a surface. Remember when we did line integrals of vector fields, we had to be sensitive to the orientation of the curve that we were dealing with, because different orientations, different directions of traversal gave us opposite answers for the line integrals of vector fields. And something similar will happen here. In formal definition, a surface that is orientable has two sides instead of just one side. So, for example, a sheet of paper clearly has a top side and a bottom side. Something like a sphere clearly has an inside and an outside. But there are also some surfaces which don't have two clearly defined sides. And the quintessential examples are the Mobius strip and the Klein bottle. Now, for the sake of using our time wisely, I'm not going to go into detail about what these objects are or why they only have one side. But I'm going to leave it to you. If you're curious, feel free to Google it or look up some videos about these objects. They're very, very famous. Now, if a surface does have two sides, then choosing one of those sides is an orientation. An orientation of a curve was a choice about whether you wanted to traverse the curve in the forward direction or in the backward direction. And an orientation of a surface is a choice of what direction is being chosen here. Are you choosing the top side or the bottom side? Are you choosing the inside or the outside of the surface? Now notice that this is basically equivalent to choosing one of the two vectors normal to the surface. You're either choosing the top side, which corresponds to the vector pointing up, or you're choosing the bottom side, which corresponds to the vector pointing down. You're either choosing the outside, which corresponds to the vector pointing outward, or you're choosing the inside, which corresponds to the normal vector pointing inward. So an orientation is a choice of a side, which is the same thing as a choice of a normal vector. Now, if your surface comes attached with a parametrization, there is sort of a standard agreed upon orientation that always comes with that. And that's to choose the normal vector. Let's call it n for short. It's this normal vector that comes from crossing R, U, and RV in the order with U first and V first. And in case this vector is not already of length 1, go ahead and divide any length that it happens to have. So this is the standard choice of orientation, the side, if you have a parametrization given to you. Alright, as an exercise, let's consider the following torus. Parameterize just as before with these equations x of u and v, y of uv, and z of uv. Based on this parametrization, determine the orientation of the torus at the point where u equals v equals 0. Does it point toward the inside of the torus or toward the outside? So let's go ahead and get into it. We have r, which is equal to x u z, and so let's calculate r sub u, the derivative in the u direction, which will change the cosine u to a negative sine u. It won't have any effect on v. It will change the sine u into a cosine u. won't have any effect on v. And since the z term doesn't contain a u, that term will vanish. And for use of v, that will change the cosine v's into negative sine v's. All the other quantities are constants and will be unaffected. But we have to be a little bit careful. In particular, I have to be a little bit careful, because if I distribute through, we have 2 cosine u plus cosine v cosine u. And in terms of the derivative with respect to v, this first term here, 2 cosine u, will just completely vanish. So we have negative sine v cosine v, cosine u, whoopsie. And we have negative sine v sine u. And finally from z, we have cosine v. Alright, now that the derivatives have been taken, we can go ahead and plug in the point that they're interested in. Remember, when derivatives are involved, you are never able to plug in the point before taking the derivative. Derivatives always have to be taken before plugging in points. Derivatives come first. Alright, so u and v are 0. So that means this entire first term vanishes. And let's see, cosine of u actually survives, and so does cosine of v. So we get 2 plus 1 times 1, 3. And if I plug 0, 0 into the other derivative, sine v vanishes, and cosine v is 1. Alright, now let's calculate the cross product. We have ru cross rv is equal to ijk, and then we'll load it up with 0, 3, 0, and 0, 0, 1, which becomes 3, 0, 0, it looks like. Alright, so let's compare that vector to the location on the torus where we're sitting. So here's going to be our xyz. And let's compare this with the technological graph of the torus, which we got from GeoGebra. Now I've gone ahead already and typed in the equation of the torus here in the upper left. And I've gone here in the bottom left and I've set u and v equal to 0. So that I can see the point on the torus that corresponds to uv equals 0. And it's here on the positive x-axis in cyan, here on the outermost part of the torus. So let me just recreate that. It's located about here on the torus. So now the vector that we have gotten from our calculation points in a direction in the positive x-axis. So it points even further out away from the torus than the point where we're at. And so, in sum, to answer the final question of this problem here, does it point toward the inside of the torus or the outside? It points toward the outside of the torus, away from the surface. And that is the convention. If you haven't been given a parameterization for the surface the same way that we were given the parameterization, and if your surface has no edge or boundary, like the torus, like the sphere, then we always just assume that we're going to choose the outside of that surface. The positive, the standard orientation, the one that's usually agreed upon, is the one that's pointing outside of the surface rather than the one that's pointing inside. That's what's just agreed. Okay, now having set up all of that preamble about orientation, we can get started talking about flux, talking about surface integrals of vector fields over surfaces. Now the notation that you'll see is the same double integral that we used for surface integrals for multivariable functions. But instead of having just the function in the integrand, you will also see this dot product dot, which comes when you're dealing with a vector field instead of a multivariable function. Okay, now having established the notation of flux, let's go ahead and demonstrate how it can actually be calculated. And just as with our multivariable functions, we're going to calculate these by translating them into double integrals. And our running example is going to be the following. Calculate the flux of the vector field f of x, y, z through the surface S, which is formed by taking the paraboloid z equals 1 minus x squared minus y squared above the plane z equals 0. Alright, so step 1 is to parameterize the surface. If you were not already given the parameterization, find a parameterization that matches the surface's positive orientation. The one that's standard, the one that's conventional. Now, what's conventional in this case, when you have the graph of a function of two variables, is to use the parameterization where x of uv is just u, y of uv is just v, and z of uv is just 1 minus u squared minus v squared. So just plug into the function the u and v that you're interested in. Okay, so now let's make a note about what values of a and of u and v are allowed. Okay, so here is our u and v, and here is our paraboloid, which I have drawn, and the values of u and v are the same as the values of x and y, which are appropriate for this surface, applicable. So u and v are going to occupy the disk of radius 1, because if z is equal to 0 at the plane, and we set z equals to 0 here, we'll be able to rearrange that to get x squared plus y squared equals 1, and then u squared plus v squared equals 1. So I'm just going to mark that that corresponds to our domain here in terms of u and v values. Okay, so now that we've found a parameterization, our next step is to calculate the following double integral. Integrate the vector field f and then dot product with Ru cross Rv. Okay, so in some sense a little bit easier than the surface integral for multivariable functions, because at very least we don't have to find the magnitude of the cross product here. We just have to dot product that cross with the function f. So let's go ahead and get started with that on our running example. So our function r, our parameterization, has u in the first coordinate, v in the second coordinate, and then 1 minus u squared minus v squared. And so if I take r sub u, I get 1, 0, and negative 2u. And if I take r sub v, I get 0, 1, and negative 2v. Okay, so let's go ahead and take the cross product of these two, Ru cross Rv, of 1, 0, negative 2, u, and 0, 1, negative 2v. Okay, So we're doing a little arithmetic here. 0 times negative 2v, take away 1 times negative 2u. And then the j component, we get a little arithmetic there. And then k comes in, and we get the k component of just 1. Alright. So now we have our vector field, and let's recall that the equation of the vector field in our running example was yxz. But again, because we are changing our integration to be in terms of u and v, we're also going to have to change these variables so that they're all in terms of the parameterization and contain only the variables u and v. Let me clean that up a bit. F of x, y, z is equal to the vector y, x, z, which can be turned into replace v for y, replace u for x, and replace 1 minus u squared minus v squared for z. Alright, so we now have our vector field in terms of our parameterization. We also have the cross product of our two partial derivatives. So let's go ahead and calculate the dot product of these two. We get 2u times v. We get 2v times u. And we get 1 times this z coordinate. Okay, let's give ourselves a bit more space. We're almost there. Okay, that's fine. All right, so now it remains for us to calculate the integral over the region D of the result of this dot product. So we have 4 times uv plus 1 minus u squared minus v squared with respect to a. And let's recall that D was the disk of radius 1. Now the idea here is that, okay, if I were back in chapter 12, and I was faced with an integral that looked like this, and a region that looked like this, I would definitely be using polar coordinates to actually calculate this integral. And that's exactly what I'm going to do here. We've used u and v to set up the integral. But at this point, this is a chapter 12 problem. Now, a chapter 12 problem. And I can change the coordinates of integration to polar if I so desire. I can think about u, remember who is x, as r cosine theta, and v, who remember is y, as r sine theta. And I can go in and I can do polar integration to actually calculate the value of this integral. So I can integrate, for example, as r goes from 0 at the center of the disk to 1 at the edge of the disk. And I can integrate as theta goes from 0 to 2 pi. I can go into my integrand and I can replace u and v with r cos theta and r sine theta. And I'll get r squared cos theta sine theta plus 1, and then anytime I see a u squared and a v squared like this, I can replace it with an r squared. And don't forget that anytime you're doing polar, you need an added extra factor of r. Okay, now let's clean this up. We got an integral from 0 to 2 pi and an integral from 0 to 1. If I distribute through r, we get 4r cubed cos theta sine theta plus r minus r cubed dr d theta. Now integrating with respect to r, I get r to the 4th power cosine theta sine theta plus r squared over 2 minus r to the 4th power over 4. And plugging in those limits now gives me the integral from 0 to 2 pi of cos theta sine theta plus 1/2 minus 1/4. Result 1/4. Finally, integrating with respect to theta, if I use a u substitution, I get u equals sine squared theta over 2 plus 1/4 theta evaluated from 0 to 2 pi, which works out to be 1/4 times 2 pi. Okay, so another lengthy ordeal, but the process is fundamentally simple, lengthy but simple. First, find a parameterization for your surface if you haven't already been given one. And then calculate the two partial derivatives of your parameterization. Take their cross product and then dot that with the output of your vector field. And then by hook or by crook, integrate the result of that dot product over the region of values of valid u's and v's. And with that, we've defined the last type of integral for the class. So at the end of today's notes, I have a summary for you of all the different kinds of integrals that we have studied and how we have represented them in terms of notation. Now, I personally find that all of these different kinds of notation are just similar enough to be confusing sometimes. And even to the extent that I seem to have made a typo here and forgotten the extra z here. Alright, for double integrals, we have our function of two variables, two integral symbols, and a dA. Triple integral has three integral symbols, f of x, y, z, and a dv. For the line integral, we have a single symbol, our function, and a ds. And if it's a vector field, then we add a dot product symbol in there. For a surface integral, we have two integral symbols and then our function. And in the case of a vector field, two integral symbols and then our vector field and then the dot symbol for the dot product. And so a summary of all of these different notations is available down here, and I'll be sure to correct that typo before I post.